a red dot?
Yeah.
We're recording?
Yeah.
Okay. Are we live? Alright. We're talking about momentum today. Today will be mass times velocity. So, momentum is just mass and velocity multiplied together. So the formula for momentum will be P. P is what momentum will stand for, or what P stands for, momentum. P equals m times v, mass times velocity. So you'll always multiply. P equals mv. Momentum equals mass times velocity. So far, so good?
No. Wait!
We'll pause there, then we'll pause. Action. Alright. The units for momentum will just be, we'll look at, if you think about the formula is m times v. Units for momentum, or units for mass, are kilograms. The units for velocity, we already know, is meters per second. So the units for momentum will just be kilograms times meters per second. So far, so good? You can't see?
Uniform.
All right. We'll pause there. The uniform. So here's the idea. Here's some ways that we can think about momentum. If you, who think, or what do you think has more momentum? You riding your bicycle, or a Mack truck going 5 miles an hour?
Bicycle.
You think the bicycle, you on a bicycle has more momentum? P equals m times v. Yeah, the truck. Why do you think if a Mack truck and a bicycle collide, right? Which one do you think is going to win?
The truck.
The truck. Why?
More weight.
More, yes. But what we're saying is mass. We're going to use the word mass here. So yeah, the truck has more mass. Okay, so if the truck is sitting still, it has no momentum. And so, yeah, it would still hurt a lot, but actually, like, if you collide into a Mack truck and it's not moving, it's sitting still, it's going to have to move back a slight amount. It won't be noticeable at all, okay? But if you had a momentum and the truck didn't, then that truck will move back tiniest bit. Not one that you would notice, but it would move back, okay? When the police came, the bigger officer had... I had heard about a story of a guy down in Woodbridge. It was like an old wrestler's like second cousin or something like that. But he was driving on a motorcycle, going like 150 miles an hour, hits an Escalade and flips the Escalade. Okay? The low mass of his motorcycle, because he had so much velocity, had a lot more momentum than the Escalade. Okay? Alright, now, school buses will always have a lot more momentum. That's one of the reasons why, or at least one of the justifications why they don't put seatbelts on a school bus. Because if a school bus gets into a car accident with another car, the school bus will barely slow down. Okay? The school bus will barely get a scratch where the car could be totaled. And the idea is because the school bus has so much more mass, then it has so much more momentum than the car that when they collide, the school bus won't have much of a change in its velocity. Okay? So students will kind of, maybe they'll fall down onto the floor, they'll hit the wall or fall down, but there won't be as much damage to them because it won't be as sudden a change in velocity than a car would. Alright, now that in mind, if you ever see, like, where there's an on-ramp going to 95 or something like that, and it's all backed up, and you see cars zipping in front of big Mack trucks, realize that those big Mack trucks are leaving that stopping distance for a reason. Because they will have a much farther distance to stop that car, or their truck. Okay, so when you see these cars, you'll see cars pull up in front of those Mack trucks because they see the room, or a bus or whatever, and they don't realize the Mack truck has so much more momentum that it's going to crash into the car. Okay, there's a reason that they have that room in between. It's because they need that space to stop. Okay? Okay. Freshman football. I used to coach freshman football. Do you want to see the way freshmen tackle?
No.
Ready? Here we go. They stand here like this. The guy runs up, and he gets knocked over, and he tries to hold on to an ankle. Okay? So then, as coaches, freshman or football coaches will tell them that you need to be the hammer, not the nail. You need to be the hitter, not the hittee. Okay? And the idea is that if I'm standing here not moving, I have no momentum. Okay? I have to be moving in. If I'm moving in and I'm hitting him, then I have more momentum because I have more velocity. Alright? In freshman football especially, you have somebody this tall getting tackled by somebody this tall. Okay? And this guy will have to win. So the idea is that this guy, even though he has a much smaller mass than this guy, he's going to have to increase his velocity. And if he increases his velocity, he can compensate for his low mass. And so this guy can end up having more momentum because it's also velocity, not just mass. Okay? Okay. All right. I'll let you copy that down, then I'll talk about it. And we'll pause here for station identification. Were you recording that whole time before or anything? Or?
No, we're recording.
We're recording now. All right.
Like dented.
Okay. Now, you will have a couple of questions on the test where it's, what is the momentum of this? What is the momentum of that? Or, what has more momentum? And I give you mass and velocity of this one or mass and velocity of that one. You will have questions like that. But much more important, and that's why we have those police, and because they use this every day, much more important than that is the fact that the total momentum before something happens, like a car accident, always has to be equal to the total momentum after that happens. So when a car accident occurs, and they can figure out how fast the car was going after it collided, they can figure out, and they'll actually put cars on the scales and get their masses and all that stuff, and they can actually work backward and say, all right, well, if I know all the momentum of what happened after, we can then say that that's the same momentum before, and they can work the scene out and work backwards to figure out how fast that car was going before it collided. Okay? So what's more useful with momentum is more the idea that whatever happens before will be equal to whatever happens after. Total. Okay? So, let's say that I am running at this student right here. And I'm going to lay him out because he's asleep. Okay? So, I run towards him. Let's make up a number. Let's say I have a momentum of 5, just to make up a number. Okay? How much momentum does he have right now?
0.
0. Right. So I have a momentum of 5, he has a momentum of 0. What's my total momentum before the collision? 5. Okay. I run into him, I throw my elbows out, I knock him back, but I get slowed down a little bit. And let's say, just to make up numbers again, now I have a momentum of 2. I knocked him back, okay, and now I have a momentum of 2. How much momentum should he have now?
3.
3. Because 3 plus 2 should add up to the 5 before the collision. Okay? The total before always has to equal the total after. Always, 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 always. Okay? Alright, now, the problem is that it's not like we have a radar gun that measures momentum. We don't have anything that can say, oh, he's going 5 kilogram meters per second. What we do measure is we can put a car or a person, whatever, on a scale and get their mass, and we can put a car or a person, whatever, we can do a speed gun, a radar gun, and figure out how fast. So we can't really do momentums, but we can do velocity and mass. So that won't work, so I'll push the button. Here's the actual equation you would use. Mass times velocity 1 plus mass times velocity 2 will equal mass times velocity 1 after he collides plus mass times velocity 2 after he collides. It looks ugly, but it won't be as bad as you think.
Did we write that down?
Please.
Yes.
Let me write this down.
So M1 would be my mass. M2 would be his mass. Okay? V1 is my velocity before I knock him back. V2 would be his velocity. What's his velocity right now?
0.
0, yeah. Now, after we collide, I'm still talking about me. I'm still talking about my velocity. So I still say V1, but the number's different. If I was going 20 meters per second here, and then I slow down to 3 meters per second there, this would be V1 prime. So this little tick mark, that little apostrophe, all it is a little mark to say, I'm still talking about me, I'm still talking about my velocity, but it's not the same number as this one. Okay, so the little tick marks just mean that the velocity will be different. Okay, I'm still talking about the same person, and I'm still talking about his velocity, but his velocity has changed. Okay? Alright. Moving on. There are 2 types of collisions you need to know. I'm going to let you copy that down, then I'll talk about it. We'll pause again. And now, a word from our sponsor. I want to be Letterman. Okay. There are 2 types of collisions. When I just knocked him back, if I was separate before, we knocked, he's separate after, then it was elastic. Alright? Elastic, E is for energy. The energy was actually conserved when I knocked him back. We didn't lose any energy to heat. Okay? But more importantly, energy, or with elastic bands are called what? Rubber bands. Rubber bounces, right? So when I knock into him, if we bounce off each other after, it was an elastic collision. Okay, now, if he was standing up and I run into him and I tackle him, and we both go together after that, that would be inelastic. We stuck together. So elastic means we were separate before, we bounce off, we're separate again. Okay, it could be this, could be this, could be whatever, alright? Whether you're separate before, you're separate after. Okay? Now, inelastic, or realize again though that energy is conserved. Energy is conserved in this case. The next one won't be. Momentum is always conserved. For all types of these problems, you'll still see momentum is conserved. Okay? That won't change. Alright. Inelastic. The only thing really different is inelastic, they stick together. So the energy will be lost. How many people have been in a car accident here? Wow. Okay. Has anyone felt the bumper or the dented area right after that collision?
It's like hot.
It's hot. Exactly. Thank you. You're the first student of this year that has noticed that.
Wow.
I'm glad you were in a car accident. Okay. It's hot. The bumper or whatever gets dented on a car will be hot because it lost energy to heat. Okay, the car is moving along, it has kinetic energy. If it crashes and sticks into something, energy has to be released. So energy was released into the bumper, wherever got dented on the car. Okay. So, a football tackle again would be an inelastic collision. Anytime you throw something and it sticks to something else, that's going to be an inelastic collision. Okay? Alrighty. I'll wait. I'll pause. We're going to practice. Okay, we'll have plenty of practice with. But I actually want you to look at them not as equations right now, but as pictures. The left-hand side will always be before. The right-hand side will always be after. Okay? So this is what happens before something happens. Whether it's before they collided or before they flew apart. This is always after. Okay? So if you look at it as a picture though, what do we see? Elastic, they bounce off, right? So here you see two things that are separate. They collide, they're separate after. They bounced off. All right, inelastic. They're separate before, they collide, and now they're stuck together. See how the masses are stuck together with the parentheses? Okay? Recoil then, what do you think recoil is? What would happen with a recoil?
It's after you do something and then you go backwards.
Well, look at the picture. What are they before, what are they after?
They're together before.
Together before, separate after, yeah. So recoil will be, they're stuck together before, then they're separate after. Okay? So with recoil, where do we know about recoil? Where has anyone experienced recoil before?
Yes.
Shooting a gun, right? So with a gun, the idea is that the bullet, or the gun and the bullet are together before. Alright? Then it gets fired, the bullet goes one way, the gun goes the other way. That's why there's a kick. Okay? Usually because the bullet and the gun had a velocity of 0 before. The bullet flies off at some ridiculous velocity. So even though the gun has a much heavier mass, it's going to shoot back in the opposite direction. Okay? But it won't be as fast. That would be very bad. If the gun went back as fast as the bullet did, then whoever shot the gun would also be shot too. Alright? Kind of like when you see in the movies where a guy gets shot and he flies back into the air. That can't happen. Okay? Because if a guy gets shot and he's flying back into the air, whoever shot the gun should be flying back also. Okay? Alright. So these are the three equations. But really it's just going to be that you know M1. Remember, notice that here are some demonstrations. Here are some ways that your knowledge of momentum will now help you in everyday life. Are you ready?
Yeah.
Great. Alright, first one. If you are going to play pool and you need to brake, you don't want to brake with just your arm. Okay? If I'm braking with just my arm, then it's just the mass of my arm times velocity that's going to brake the rack. Okay? So if somebody's going to do a good brake, they get their whole body behind it. Instead of this, they're going to get their whole body behind. Okay? Because now it's just not the mass of my arm times velocity, but the mass of my whole body times velocity. So the ball will go much faster because all my momentum will get transferred to that ball, not just the momentum of my arm. Alright? Baseball players, the same idea. When a pitcher is going to throw, he doesn't just throw with his arm. He throws with his whole body, right? The idea again is that his whole body is moving, and all of that momentum of his body is now getting transferred to the ball, which is why it goes faster. Okay? Alright. Now, more useful tips that you can use in everyday life. If you're in a bar fight. Alright. With punching, boxers don't punch with their arms. A boxer doesn't punch like this. Okay? Because it's the momentum of just my arm, okay, the mass of just my arm isn't enough momentum. Even if you have big guns like me. Okay? Yeah, that's right. Okay, so instead of just the momentum of my arm, I want to use the momentum of my whole body. So that's why boxers always have to step into the punch. Instead of just having mass of this arm times velocity, they're going to do mass of the whole body times velocity. That means there's more momentum transferring to his face. Okay? So boxers will always be told to step into the punch, to use their whole body. Even with wrestling, like if we want to chop out an arm, I'll tell the kids, because some kids will just try to do this instead of throwing their body behind it. And it's always going to be better if you throw your body behind it. Okay. Don't ever play baseball with a semi-deflated basketball. Learn from me. Learn from my mistakes. Has anyone tried that before?
Yeah.
Okay, learn from Devin's mistakes too. All right.
Nothing will happen.
So, this is what happened to me. I was in 8th grade, and I was just playing with my friend. He throws a ball like that, lobs it to me like softball. I have my aluminum bat, I swing at it, and it flies right back in my face. I go to the ground, I come up right away, and everyone's like, oh, let me see. And I have a mouse like that big over my eyes. No, I wasn't, but I probably should have been.
It's a headshot. You're not
I got smacked right in the eye. And so, and the idea was that the momentum of a basketball, because there's so much more mass behind this, all of that momentum transferred to the bat and transferred right back. Okay? If it was a baseball, the ball would have gone the opposite direction. Because it was a basketball, the basketball barely even stopped. It didn't go anywhere. It just went, stop right there, and then my bat went straight back into my face. Okay? So learn from my mistakes, please. Alright, you want to see? Here's a demonstration. Let's bring the camera. Go ahead and pause it. Alright, here we go. Here is, watch how high up this tennis ball goes. Is that getting in the shot?
Yeah.
Okay. So about that high. Okay, watch how high up the basketball gets. About that high. Alright, one more time. About there. Alright, now, I want you to watch how high the basketball gets this time. Ready? Did you watch the basketball?
No.
Let's try it again.
What's the ball? Goes down.
See how high the basketball goes up this time.
Not that high. That's good.
Basketball didn't go as high, right?
That's a good way to throw.
But the tennis ball went much higher. Why?
Because the basketball transferred its energy.
What's the word we're talking about today? Momentum. So the basketball transferred its momentum to the tennis ball. So this had a lower mass. This transfers its momentum, and it goes much higher velocity on this. Shoots off in the room. Okay?
What about if you put a paper on it?
Oh, yeah.